Now, this is what we mean by having some idea. If I'm going to throw a stone, it reaches a certain distance. I throw it slightly differently, it's not going to zoom off to infinity. It's just going to stay pretty much close by. In the nonlinear world, things happen very, very differently. And the story goes back, as it happens actually, it's 50 years ago this year. There was a meteorologist called Ed Lorenz at MIT who was trying to simulate the weather. So the question that he was asking was, can I write the equations for the weather in some approximate way, and can I study it on a computer? Part of the lore, these equations are really very simple. He was looking at the circulation in the upper atmosphere. X is some velocity field, Y is a pressure field, and Z is a temperature field. And we know that in the upper atmosphere, the ground is at a particular temperature. The upper atmosphere is colder. So you have air that rises and it circulates. So these equations are an expression of that particular circulation. And what Lorenz did was to put this on a computer, and all of you could, and try to find the solution. Now, part of this is the way in which it was discovered, and this really did happen. In those days at MIT, you did your calculations, and in the evening you switched off the computer and you went home. Pretty much like what we do even today in many, you don't let your computer work overnight. You never know when there'll be a spike. But in those days it was a real requirement. Also, 1963 is before computer graphics, before a lot of stuff. So what Lorenz did was to do a calculation one day. He stopped, and the next day he would come back and start from where he stopped and go on. On 2 consecutive days, he actually started from the same point that he had stopped a day earlier. And what he found was that these 2 solutions that he got, which should have been identical, they were identical for a little while, and then they became very different. Okay, so you think you've made a mistake, you go back and you try it again, and again you discover that it agrees for a little while, and after a while it changes. And then he was able to trace out the origin of the problem. Because his starting point was only specified till 4 decimal places, on 2 different days, the decimal places after 4, which is there on the computer, the 5th, 6th, etc., those were very different. And to give you an idea of what it was like, so these are the 3 equations, and what he did was to start at, let's say, the black point on day 1, and this point, when you take the solution, this is how X, Y, and Z change in time. So on one day you follow I hope you can see the red curve. On the second day, you started at what you thought was the same point, but there was a very small difference. And that very small difference was in the 5th decimal place or even higher. But for a little while, the solution looked the same. For a little while, it looked the same, but after a while, the blue curve separated out from the red. And so on one day you get the red solution, and another day you get the blue solution, and all you've made a difference of is a negligible fraction out there. Okay? This property, it's also fortunate for us that it was a person who was meticulous like Lorenz who was doing this work, but this is a completely accidental discovery, and this is the beginning of what is now called chaos theory, because the property that Lorenz had discovered is what's called sensitivity to initial conditions. A small change in your initial conditions, and it's like so, you start over here, and let's say this is where you would go, but you start a small distance away, and you would end up somewhere else. Now, as a metaphor, this is something which is very attractive because we are all aware of situations where a smallest change of something affected the outcome completely. But here it is happening in a set of mathematical equations, but this is again part of the reason why we all like the idea of the chaos theory, is that a small change has got huge consequences. And this property is actually formally, it's a mathematical property called sensitivity to initial conditions, and it is the heart of what is chaos theory. Again, just as an instruction, this sensitivity to initial conditions is not, it's not even that unusual. It's just that we don't always recognize it. And I'll just go through a little tutorial over here, which actually I have taken from one of the people who was the founders of this field. If you just look at the following mathematical transformation, and for the non-mathematicians, I'll just explain it. You take a number x, you multiply it by 2, and the modulo 1 means that whatever part is bigger than 1, you just consider the portion of the answer which is below 1. So, for example, if I take 1/3, I multiply it by 2, it's 2/3. And if I multiply that by 2, it's 4/3, but I subtract 1 because 4/3 is bigger than 1 and I only look at the part which is below 1. So I get 1/3 again. And then, of course, it's going to double. It'll become 2/3. It'll become 4/3, which is actually 1/3, and so on. Okay? So we know exactly what happens if you start with a third. You get 1/3, 2/3, 1/3, 2/3, 1/3, 2/3. Now, what happens and typically if I ask what is 1/3, you'll say, 0.33. Right? So you start with 0.33, double it, 0.66. So 0.33 was 3 parts in 1,000. That was the error. 0.66, the error has become 6 parts in 1,000. Double that is 1.32. Remove the 1, so it's 0.32. And now the error is actually 1 part in 1,000. 1 part in 100. Double that, it's 0.64. The error is 2 parts in 100. Double that, and the answer is 1.28. Remove the 1, it's 0.28. And now the error is 5 parts in 100. It's double it. So you see how quickly the errors have just accumulated, even though initially you didn't start you thought you were just, 3 parts in 1,000. What difference can it make? This is the power of nonlinearity, and this is what sensitivity to initial conditions means. In various systems, we see this over and over and over again. Small changes in your initial condition, what you think is not important, and it has huge changes in consequences. Because, after 6 times, your answer is 0.12. It's neither like 1/3 nor like 2/3. It's completely different. So, this is chaos. What we mean by chaos in a technical as well as in a non-technical way is when you cannot predict anything. But why can't you predict? Because the system has sensitivity to initial conditions. And why does it have sensitivity to initial conditions? Because it is nonlinear. Okay? So this, in a sense, is really the summary of almost everything that I want to say. I'm going to say a little more, though, Professor Velukar, because I've prepared a few more slides. This was not all that Lorentz discovered. Because even though you have the difficulty of making predictions, yet it is possible that if you start, what is possible is what Lorentz also recognized was that while you started over here, you went on the red curve, close by you went on the blue curve, and you went anywhere else, you were still in the same general region. Okay, It's not as if you started over here and you went on this side, and you started a little far away and you went away on the other side. If you started over here, you went on something, and if you look long enough and look fondly enough, it looks like a thing. Okay? And this thing is what he discovered, is the idea of an attractor. That is, if you start with one set of initial conditions, you go on to the same part of space. All right? You start here, you go to this attractor. You start here, you go to the same attractor. This idea that the system has an attractor is again a very important idea, even though you cannot actually make any very precise predictions on it. Especially when you deal with the weather and stuff, you have a very good notion that there is an attractor without being able to make very precise observations, predictions. Okay. It's not just at a qualitative level that you can do all this very quantitatively, and that has actually been some of the excitement of the field, that you can measure the rate at which the sensitivity to initial conditions is displayed, and it gives rise to something called the Lyapunov exponent. Okay. As I said, regardless of where you start here, you go on one curve, you start somewhere else, you'll go on something which occupies the same space. This is the idea of the attractor, and also what Lorentz called the butterfly effect. The butterfly effect is not to do with the shape of this attractor, although it's just a coincidence that the attractor of this system looks like a butterfly. What Lorentz meant by the butterfly effect is really what we've seen with that little example. He was giving a talk on the difficulty of predicting the weather, and so he says, these equations are so nonlinear and so complex that it is as if the errors inherent in the effect of the flapping of a the wings of a butterfly in the Amazon, by the time the solution reaches New York, that creates a snowstorm. Right? I mean, it's a metaphorical idea, not necessarily that the flapping of the wings of a butterfly in the Amazon creates a snowstorm in New York, but this is how the errors, or this is how the unpredictability changes, that with very, very small effects over there, it can have huge consequences. Okay. It turns out that this is one of the reasons why weather prediction is so difficult. Such chaos underlies the very system that we use in order to discuss quantitative approaches to predicting the weather. As of today, the best science that goes into weather prediction uses some amount of chaos theory, but a large amount of observation. Okay, it turns out that it is really very, very difficult to continue solutions for very long because of nonlinearity. Another idea which is there in these systems, somebody should tell me when we are drawing towards the end. All right? It's not as if a system is either one or the other. Okay? It turns out that many systems contain this feature within themselves, that as you change a parameter in the system, it can go from being in the regular and therefore predictable mode to being irregular and therefore unpredictable mode. And equations like this have been used in modeling populations, not human populations, but in modeling populations of fish or of a variety of different kinds of systems, including flies and so on, small, contained and well-studied populations. This equation comes out of population biology, and an equation like this is extremely simple, but as you can see, it is nonlinear because it has the x squared term, and this has been used as a paradigm for nonlinearity for many years now. I'm not going to go into too much detail, but what we know about this system is that as you change the parameter, as you change this parameter r, you can go from something which is periodic in time to something which doubles as fast, then that doubles, and so on. So you go through the period going from, let us say, 1 in some unit, to 2 in that unit, to 3, to 4, to 8, and all powers of 2 all the way up till infinity. So when something becomes infinitely long to recur, we call it aperiodic. It doesn't have a period. And that's another way of thinking about chaos. Phenomena that never repeat themselves. So one aspect is the sensitivity to initial conditions. One is that it never ever repeats itself. There are other ways of looking at it as well. Okay, so there's some things that one can play with on a computer. All right. In that sense, chaos is linked to unpredictability, because if a given phenomenon is not periodic, it's very difficult to predict it precisely. Some of you would have seen this picture before, but I'm not going to go much into it. One of the main reasons why we all study it is that this behavior is universal. Meaning, you find it in all areas. The way in which a flow, when you open a tap and that flow becomes turbulent, and the way in which the heart goes aperiodic during arrhythmia, all these seem to share same common features. How a population oscillates chaotically, how the Lorentz system goes chaotic, how the heart goes arrhythmic, all these have common features, not everything common, but many common features, which makes it easier to analyze and to study. The way in which a pot of water boils, much of the physics of that is the same as how the heart goes chaotic. So you can see that if you understand one system, you start having an influence on trying to predict other phenomena as well. Okay. So let me summarize. Most of the systems that we are surrounded with and that we deal with are nonlinear, but we make approximations, and sometimes they don't obey those approximations. This sensitivity to initial conditions is what we call chaos. And the physical manifestation is that things are difficult to predict precisely, and sometimes you have to ask other questions, maybe statistical questions, or probabilistic approaches. Those are when one has to learn when the approximations break down. Okay. Takeaway message: what is chaos? It is just the ability to display sensitivity to initial conditions. And as I end, let me come back to the question, or at least one of the questions I started with: is the solar system stable? For most of us, the sort of immediate answer is only important for the next 100 years or so, right? I mean, we're not that worried about, or maybe we should be worried. It's a matter of genuine concern from a sort of a theoretical point of view in some ways. We've been orbiting the sun for so long, but how long will this go on? And it turns out that we've got a laboratory where we can see some of the, see the effect of stability or instability. One of the planets in our solar system is Saturn, and that is a mini solar system in itself, in the sense that it has got a large mass at the center and many smaller masses around. Now, in the way in which we are going around the sun, these particles are also, or these little, whatever there is in the rings of Saturn, are mostly, it's mostly just material. It's, I don't know whether to call it earth or mud or whatever, but it is, rocks. It's stuff that is going around Saturn. And like we are in a disk around the sun, all this matter is also contained in a disk. All right? That's just angular momentum conservation. But what we see, which is very interesting over here, is that matter is not uniformly spreading outwards from Saturn. Even though it's in a disk, it is not all uniform. A very characteristic feature is that there are gaps. And some of you who might have seen Saturn and seen the gaps in the ring, this is one of the most characteristic views of Saturn, has been described for several centuries now. So what are the gaps? What's over here are rocks, particles, and the gaps are where there are no rocks and no particles. The gaps is where there is the absence of material. So what happened? It turns out that this is an example of what unstable behavior is. Any particle or any rock which was in the gap, as it went around Saturn, it was on an unstable orbit and it just went away. In fact, most of, when we can sort of imagine that when the solar system was formed, there were many more planets. But many of them were on unstable orbits, which eventually left our solar system. And what we have remaining are not the only stable orbits, but the most important ones, and that's where all the planets are located. So the stability of the solar system, even though it starts out as a question which may seem of only limited interest, is really very important to us. The whole solar system is not stable, just as all of Saturn is not stable. There are many, many unstable orbits all over there. But we occupy a very important one, and which is why, in a sense, we are here to talk about it. And that is the importance of the field, that we know what is chaotic, what is sensitive to initial conditions, and what is unstable, and what is not. Okay. So let me thank you for your attention, and be happy to take questions.